afternoon, everyone, and welcome. Today, we are going into a subject that sits quietly behind almost everything we call the future, and yet most of us have never once thought about it. Electric vehicles, wind turbines, robots, defense system, the whole clean energy transition. We talk endlessly about batteries and chips and hydrogen. But there's one small hidden component that makes all of it actually move, a permanent magnet, often no bigger than the palm of your hand. Here's the striking part. One country, China, controls almost the entire supply of these magnets, from the ore in the ground to the finished product. In 2025, that control became so real that car makers around the world were forced to slow or shut down their factories. And India, which holds some of the largest rare earth reserves on the planet, still imports almost every magnet it uses. So, how did a few grams of metal become one of the most strategic technologies of our time? Can India actually break free? And what would it take to go from owing the sand on our beaches to owing the magnet inside the machine? To help us understand all of this, I am delighted to be joined by someone who has spent over 3 decades on the shop floor of India's biggest steel and metal plants, and who has thought very deeply about this exact question. He calls the journey from mineral to magnet to machine. We welcome you, Mr. R.B. Shridhar, sir.
Thank you.
So, sir, starting with the first question, you have spent 33 years on the steel and metal shop floor, running some of the India's biggest plant. What pulled a steel man into the strange little world of rare earth magnets?
Look, most of our customers are like wind or electric vehicle. All of these people use permanent magnets. And if there is any disruption in their permanent magnet supply, then what happens is their factories stop and our demand falters. So having said that, it is sort of an ecosystem which we are all tied to each other in a big way. And for India, this is a very important segment where we have not concentrated on. India has the third largest rare earth reserves in the world. However, we hardly process anything. There are 4 types of processing. One is, of course, the ore itself. Then what we do is we sort of refine it and separate the ore, make it into concentrates and oxides. Thereafter, we take it to alloying, and then we do sintering. So these are the 4 or 5 processes. After sintering, we get the magnet. We do what is called the qualification. It's very important that we produce not the commodity grades magnets, but different ones, which are the high value added stuff and all that. Now, if you look around, whatever you do, permanent magnets are a part of it. For example, electric vehicles, for example, your defense and aerospace and wind turbines. Earlier wind turbines, how the wind turbine goes. You have a rotor. Rotor is connected to a low speed shaft. And that is connected to a gearbox. Gearbox amplifies the low speed into higher speed, and then you have a high speed shaft which connects to a generator. So low speed shaft from the rotor, gearbox which amplifies the speed, and then you have a high speed shaft, and finally the generator. Now what we have come up with an innovation is, why don't you connect the rotor directly to the generator? That is to say, obviate the need for a gearbox and all that, remove the gearbox altogether. This can be done through a permanent magnet. Okay. Now, so all these permanent magnets is going to be used there. So I said to you about wind, defense and aerospace, then all the missiles which we do, the fin actuators in those missiles are rare earth magnets, and all the robos and all these joint actuators for robos, they're all rare earth magnets, permanent magnets. And then compressors in heat pumps and all, they are permanent magnets. So they're permanent magnets, and the magnets themselves are omnipresent everywhere. Now, let's say there are 4 types of families of rare earth magnets. First one is your what we call it as the normal one, ferrite ones and all, where hardly any rare earths are used, permanent magnets are used. It's basically what Ola and the TVS use. So it's an innovation because you obviate the need for a rare earth magnet. Then you have the neodymium, iron and boron. This is the workhorse. Neodymium, boron and iron. So this spawns nearly 70 to 80% of all permanent magnets which were here used. Now this is the second variety. Then you have the samarium cobalt, which is the third variety. The last one is your bonded neodymium ferroboron. So this is the last one. What happens is, in certain sensors and all that, complex shapes, intricate shapes and all, which normal sintered magnets cannot be matched into. So you do what is it? You powder the magnet, put some polymer in it, and you bond the polymer and the magnet together and produce complex shapes, those which can be customized to various sensors and all that. So that is the bonded polymer permanent magnet. So you have all of these sort of things. Now, even in this permanent magnets, you have the what rare earths go into it. You have got the light rare earths and you have got the heavy rare earths. Light rare earths are neodymium, praseodymium, and those sort of things. And you have the what we call the heavy rare earths, which is your terbium, dysprosium, and so on and so forth. Samarium. So these are some of the things which we should know. The total size of the permanent magnets at this point of time is about $20 billion, and it is growing at the rate of 9%. By 2033, it is estimated that it's going to be almost double, $40 billion and all. So there's a lot of growth. Unfortunately, 90% of all the what you call as separation, refinement, alloying, sintering, all of this is done in one country, that is China, as you rightly said. Sometimes even 94%. Okay, whereas China is holding only 60% of the rare earth reserves in the world, but still the processing is almost 90 to 94%. And out of this entire production, 65% comes from one country, that is Myanmar. So should we not have good relations with Myanmar and get those rare earths from there? So this is one important point, critical insight for the audience, which I would like to say. Even if we were to get those rare earths from Myanmar, the rare earth oxides and the ore and all that stuff, do we have the processing capability? Now, this is something which should be put at God's speed. We have to, as a national sovereignty issues with regard to China. Then, who are the major suppliers of rare earth magnets in the world? Of course, let's talk about the Chinese. You have the Baotu, then you have JL-MAC, then you have the Japanese ones like the Proterial, and then we have Shin-Etsu. So that's another big one. And then, of course, Vacuum Schmelz, which is in Germany. So these are some of the major rare earth magnets which we have around the world. Yeah.
Very rightly so said, and I think the highlight of the Myanmar was one of the key point for the audience. So moving to the next question, everyone talks about batteries, chips, and hydrogen. You argue the real hidden choke point of the whole energy transition is something most people have literally never thought about, and a magnet you could hold in one hand. Why?
See, what is electrification? It's conversion of energy into motion. What is motion? It's motors. And what is motors? Rare earth magnets. Okay, so this is the link. Electrification, motors, rare earth magnets. And these rare earth magnets, motors, are there in electric vehicles, they are there in wind turbines, then you have it in, as I mentioned to you, in defense and aerospace, then you have in various applications, and also the simple ones like the fans and, all this, the daily equipments, white goods and all that, so they have motors. So these are a lower variety of motors. So when we talk of this is these are the permanent magnet uses and all that which we have. Now, very importantly, why this has got more prominence and relevance nowadays? It's like this. If you have a tooth, nobody notices it. Only when it starts aching do you have a problem, when you recognize that there is a presence of tooth. Similarly, the same thing with magnets also. In 2025, China started, what you call as licensing it for it. In 2025 October onwards, they started licensing the heavy rare earths. Now, heavy rare earths, I would mean dysprosium, terbium, samarium, and all those sort of things. So light rare earths are okay, you can still import. That is to say, neodymium, and then what you call as praseodymium, all of this you can import. But then you require heavy rare earths as well, otherwise you have a problem. Okay, so this is what has happened. We have realized that, one country is almost having a chokehold on the rare earths worldwide. So we have realized this now. People are taking the necessary steps to come and resolve this problem.
So I think your example was very apt that until unless we have truth, no one notices it. Once it is not there, we notice it. So I think the things which we don't have, the technology or the things and on which we should all work on it. So moving to the next, make it real for us. If I'm driving an EV or standing under a wind turbine or watching a factory robot, where is the magnet and why does nothing move without it?
Look, magnets have got three properties. Let's start with that. Some called remanence, then you have coercivity, okay, and then you have the energy product, which BHmax that's called. What is remanence? If you put a magnetic field, okay, and if you remove the magnetic field, magnetic flux, if you remove it, the magnet which is there should still retain its magnetism. Even after you remove the magnetic field, it should retain its magnetism. That's what happens with the neodymium iron boron magnets. I'll come to that a little later. Then the second point is coercivity. If you have a magnet and if you put mechanical stress on it, like high RPM, which happens in electric vehicles and all that, very high RPM, then what happens under those mechanical stress, some of the magnets can demagnetize. Then thermal instability, high heat and low heat, thermal cycles and all that stuff. And then demagnetization load, etc. So all of these things, and sometimes the adhesives, inside the magnets fail. Under these circumstances, the magnets can fail. If you put an anti force against these magnets, they start demagnetizing. Okay, now the resistance to demagnetization is called coercivity. First is remanence, that is to say, if you remove the magnetic field, whether it still retains the magnetism. That's one. The second thing is, if you put reverse forces, if you try to demagnetize the magnet, how much of magnetism it can still retain. It is resistance to demagnetization. That's the second one. Third one is your power density or energy density, what is called as BHmax. How much of power and energy it can give in a small volume. So it is put as so many joules per meter cubed. Okay, so that means it gives you compact motors. Okay, now what happens is, if you use a permanent magnet, you do not have to use a huge magnet. You can use a smaller magnet. It's a compact size. Let's go to remanence. What happens in remanence is it's a torque density. BHmax is power or energy density, whereas remanence is your torque density. Applying some torque, how much of applying this field, how much of torque you can generate. So torque per kg, how much of torque can be generated per kg of the magnet. That's what is the torque density. So the remanence is that. Okay, now let's talk about the various magnets which I mentioned. I talked about the ferrite magnets. Then I talked to you about bonded neodymium iron boron. Then I talked to you about samarium cobalt, and then I talked to you about sintered neodymium iron boron. So these are the four families of Let's talk about the BHmax. What is this energy density? The energy density is maximum in the case of sintered neodymium iron boron. So that's the as I mentioned to you, the workhorse. The energy is 400 kilojoules per meter cubed. The second one is a samarium cobalt, which has got an energy density or power density of 250 kilojoules per meter cubed. That's the second one. What does it mean? In a small compact size, it can give you more power and more energy. Then you have the bonded neodymium iron boron. What did I say is this bonded? You put polymers and magnets together, and this will take complex shapes. All the sensors and all are very complex shapes and all that. So if you want to fit a magnet into that, you just have a complex shape. It can be customized to any shape. So that can be possible by a bonded magnet. Now this energy density comes down, it is 80 kilojoules per meter cubed. Last one is the ferrite ones, which Ola or what is the other one, TVS use in the two-wheelers and all that stuff. That's 30 to 40 kilojoules per meter cubed. So this is the energy penalty, the maximum and the lowest. Then let's come to the temperatures in which they operate. I said many good things about neodymium iron boron magnet. But then after 80 degrees centigrade. Most of these electric vehicle motors and all, they operate anything between 150 to 200 degrees centigrade and all that stuff. That's the thermal level which they operate. Under those thermal levels, what happens is this neodymium iron boron magnet starts getting softer. From 80 degrees itself, it starts getting softer. And by the time 150, 160 degrees comes, it becomes much, much softer, and all the permanent magnets are lost. The permanent magnetic field is lost. So that is one. What do we do to arrest this? So this is where it comes. You add heavy rare earths, which is dysprosium, terbium and all that. If you add dysprosium and terbium to this neodymium iron boron magnet, you can increase the temperature coercivity, ability to withstand higher temperatures up to 200 degrees centigrade. Please, this is a critical insight which people should know. Why do you require heavy rare earths? With this lighter rare earths, which is neodymium, you can, the magnet starts softening from 80 degrees onwards to 150. So it may not be usable in an electric vehicle because the RPM is huge. And the temperatures are 150 to 200 degrees centigrade and all that. So to withstand those temperatures, you require heavy rare earths. Now, if you introduce heavy rare earths, it has got a penalty. What is the penalty? The penalty is, this dysprosium is anti-parallel to iron. Okay, there is a little bit of technicalities which your audience must appreciate and also must note. Now, if you add, dysprosium into a magnet, it is anti-parallel to iron. So what happens is the magnetic field is curtailed. The remanence comes down. If the remanence comes down, if the magnetic field comes down, what happens? Your torque per kg of magnet comes down. What is the torque per kg? If you want to accelerate, you will get a quick acceleration. Or if you have a robotic arm, it has to lift its arm up and down, you get a much quicker motion if you have a higher torque density. Now, if your remanence, all this is possible because of the attribute of remanence in a magnet. Now, if you reduce the remanence, what happens is because of dysprosium helps you in the higher temperature stability, but then it reduces the remanence. So the torque per kg comes down drastically. So that's one negative. The second negative of dysprosium is it's all dependent on China. China has licensed this product. So one is the physics problem. Second is the geopolitical problem. So that's where, you have this dysprosium coming into play. Now, so I mentioned to you, samarium is also under license. Samarium is another heavy rare earth. It's also under, but then it improves. Samarium can tolerate temperatures of 350 degrees centigrade. So if neodymium boron magnet has got a problem and it softens around 80 degrees, and therefore you have to add dysprosium and all those stuff. Okay, and to increase it to up to 200 degrees centigrade, it can, even after that, it can withstand up to 200 degrees centigrade only. But samarium, cobalt can withstand up to 350 degrees centigrade. Now, this makes it very apt and relevant for all the space, actuators and defense, applications and all that stuff. Then the third one is your, this bonded NdFeB, where neodymium iron boron, whose temperature tolerance is around 100 degrees centigrade. Okay, and then your ferrite is also around 100 degrees centigrade. So ferrite and the bonded ones are around 100 degrees centigrade. Samarium cobalt is at around 350 degrees centigrade. The normal neodymium, one is around 80 to 100 degrees centigrade. But however, if you add dysprosium, it goes up to 200 degrees centigrade. This is the temperature, what you call it as a resistance which can do. So these are some of the things which you should note. And dysprosium is highly dependent on China. How do we do to reduce the dysprosium dependence? That's as we go along, we will discuss that. So I mentioned to you about light rare earths. I mentioned to you about heavy rare earths. And then how are these things used in India? Okay, that's your question. How are these things used in India? Now, let's put it this way. I mentioned to you dysprosium has got a physics problem. It has got a geopolitical problem. Okay, of course, it improves the temperature resistance. Can you bring down the dysprosium content? Right now, 5% of all the magnets have the dysprosium content to withstand temperatures up to 200 degrees centigrade. We have unique, innovative ways on how we can reduce that 5% to 1 to 2%. That we will discuss as we go along. So this is one critical insight. How do you, optimize the use of dysprosium? Okay, there are many companies in India have already done that. You have the Chara company which uses what is called as switched reluctance motors. Okay, so where the dysprosium and the heavy rare earths and all can be brought down. Then you have what is called as ABB in Germany. These people also, and in fact it is also done in India. They also supply what is called as synchronous reluctance motors, where the usage of dysprosium and heavy rare earths and all is brought down. Then you have simple energy, which does not use any rare earths at all. Okay, and then you have Ola and TVS, which I have already mentioned to you, which uses ferrites, which don't use rare earths at all. And then you have Enercon. This is another company which optimizes the use of rare earths through a different mechanism. It's called the windings and the number of poles of magnets and all which are used, which we will come to it as we go along.
Okay, sir. Very briefly explained, and it's very technical. I think it will be very helpful for the people who are in this industry, in this sector. So, sir, we are moving on. China doesn't just mine rare earths, it controls almost the entire chain. And in 2025, that turned into a live weapon that shut car factories down. What actually happened, and why do you say owing the ore is the least important part of the story?
Look, owning the ore is also important. You will have to, sort of mine it. There's a lot of effluents which are involved in it. Why the Western world has given up on, mining rare earths and all that? Because it involves a lot of effluents, environmental considerations and all, which is not a problem in China. But moving from there, what is the next step? Next step is refining and separation. China is the master of that. Then alloying. As I mentioned to you just now, there are various alloys which you have to add. You have to add aluminium, you have to add copper, you have to add, what you call indium and those sort of things. One of the things of this neodymium, iron boron magnet. For short purposes, I will not say this is a mouthful. Neodymium iron boron is a mouthful. So I'll just say neodymium magnets for the sake of brevity. Now, what happens is they are having corrosion problem. They also have what is called as a coating problem. Okay, they are also brittle. They are brittle. They are corrosive. Of course, there is a geopolitical problem which I have already mentioned to you. Then, of course, you also have the situation of softening with temperature. Now, in such cases, what you had a lot of alloys, aluminum alloys, copper alloys, indium alloys, and all those sort of things to improve the corrosion resistance, to improve the coating. So the indium also is added. So alloying, and there are different types of alloys. Samarium cobalt. Okay, so that's also one alloy. So as I told you, samarium cobalt can help you withstand temperatures up to 350 degrees centigrade. It is used in all the actuators in missiles and aerospace and those so on and so forth. So China specializes in separation, refinement, alloying and sintering. Okay, the entire value chain, end-to-end ecosystem of magnets, China is a master of it. I have given you the example Baotu Complex and JL Mag. They are the big companies which are in this. And above all, qualification. If you do not want to be in the run-of-the-mill, sort of commodity segments, you are a commodity producer. Okay, you are in the game till the next tender. Today you won a tender. Okay, and you have supplied. The next tender, it will be done again, and then it will be the lowest bidder. So you are only measured on price. You are only measured on what is the cheapest Chinese supply is. You will be benchmarked against that. So if you do not want to be benchmarked against the cheapest Chinese supply, or you do not want to be benchmarked against other cheap producers, and you also are exposed to the lot of raw material uncertainties and vicissitudes and all that stuff, then you have to get into the superior high value magnets and all that. So that's with the qualification is required. Okay, so in the entire China specializes in almost all of these things. Of course, Japan is a master of this also. Japan has done a lot of work on qualification, on material science. We will discuss how much of innovation China has done. In fact, one of their companies, Japan has done. One of their companies, Proterial, is now setting up shop in India. Okay, which was earlier Hitachi Metals and all that stuff. So, in qualification, in material science and reliability, Japanese are experts. Okay, I have given you an example of Shin Etsu and Proterial. These are the ones who are leading it. So Qualification is also important. There is another thing which we should note. India also produced these rare earths in the past to an extent, but then the Chinese have got a peculiar strategy. They dump materials in such a way, they started dumping these rare earths oxides and all between $18 to $32 per kg. Obviously, with such low prices, we were not competitive and we closed all our businesses, like what the Western world has also done it. But the government of India is now coming up with a beautiful scheme. It's a 7,280 crore scheme, which would supply 6,000 tons of all these rare earths oxides and all to 5 bidders. Okay, and they will be given compensation 90% on actual sales, not on capital. Because if you do give it to them on capital, you have white elephants, they may not even be working, and then they may not be having sales. So it is tied to the sales, and 6,000 tons per year for 5 bidders. And IREL will be supplying, which is the government agency, will be supplying neodymium, praseodymium oxides to these people. Just for one more interesting point, now this IREL was supplying these oxides and all to Japan. Now they have stopped that. They are going to reroute all of these, oxides, concentrates and all to Indian producers, so that, India has this, what you call as the Indianization and indigenization of all this entire value chain.
Okay, so here's the paradox that gets me, that India sits on the third largest rare earth reserves in the world and still imports almost every magnet it uses from China. So how do you own the treasure and still stand in the import queue?
That's what I said. No, unless we, the entire ecosystem, right from, separation, what you call refinement, alloying, sintering, qualification, unless we own this process, we will not be able to do. Government has taken a step. This 7,260 crores. Let me see how many people come into it. Already Midwest has come up. Then there are many others who are coming up, with this. So let's see what happens now.
Okay, so let's see. Hope for the best. So next is as you have mentioned, and you say that every magnet ever made comes down to just 3 numbers. For a listener who is not an engineer, what are they, and why does an EV company lose sleep over them?
Look, the 3 numbers are Remanence, which is written as BR, then energy product, BHmax, and then the third one is coercivity. I've already given you. What is Remanence? It's basically the torque density. Okay, now how much of torque per kg of permanent magnet you can produce? So if you produce more torque, obviously you can accelerate more, the car can accelerate more, and then robotic arms can move their up and down much faster. So this is what is meant by Remanence. Now again, if you remove the magnetic field, how much of magnetism it can retain? So that is Remanence. Then that's basically magnetic field. Second one is a coercivity. Resistance to demagnetization. By demagnetization, resistance could be thermal, it could be adhesive, durability. All these magnets are bonded to the systems through adhesives. Adhesive durability is also an issue. Mechanical stress. Okay, at high RPM, which happens in electric vehicles, demagnetization load, long-term reliability. So all of these is under coercivity. Okay, then we have the energy product max. Now here I would like to talk about the comparison between energy product max, which is your BHmax, that is the power density or the energy density, how much power and energy it can give per meter cubed. So if you have more power, obviously it can be miniaturized, it can be made compact. So that's what it is. Now if you look at it, BHmax for sintered neodymium magnets is 290 to 400 kilojoules per meter cube. This is the highest. Followed by samarium cobalt, which is 200 to 240 kilojoules per meter cubed. Ferrite is low, 25 to 40. No, you can remove the rare earths from it, but then the kilojoules per meter cube comes down drastically. So that means your magnets have to be much more. The volume, it has to be more to compensate for the loss of the power density. Okay, then you have the bonded neodymium ones, which is about 60 to 100 kilojoules per meter cube. So this is one metric which I mentioned to you. The second one is the remanence. Now remanence is, as I told you, if you remove the magnetic field, so how much of magnetism is retained? That is in Teslas. So remanence is 1.2 to 1.4, Teslas for sintered neodymium magnets, which is the highest, followed by samarium cobalt, which is 0.9 to 1.1. Ferrite is very low, 0.3 to 0.45. And then bonded NdFeB, that is bonded neodymium magnets, is 0.6 to 0.7. And the temperatures also we have talked about, the ranges in which they operate. Corrosion, this is important. This neodymium magnets, iron neodymium, iron boron magnets are very poor, needs coating. They are corrosion prone. Now, samarium cobalt magnets are good in corrosion. Ferrite are excellent in corrosion. And so ferrite, when it loses on the power density and also on the remanence, but however, it makes it up on the corrosion side. And bonded NdFeB is also good in corrosion resistance, but not excellent as a ferrite. Okay. Now the cost. The sintered neodymium magnets are the highest cost. Samarium cobalt is slightly higher than this also. The lowest cost are the ferrite ones, and the bonded neodymium ones are the medium cost. Where are these things applied? These 4 families, where are they applied? Sintered neodymium magnets are in EV tractions, wind, servo, and all those. Where I mentioned to you about wind, where are they used? It's used in this direct drive wind, generators and all that stuff. There it is used. So, samarium cobalt is aerospace and defense, because they have to withstand higher temperatures, higher temperature engines and all that. Ferrite ones are appliances, pumps, fans, which is the normal daily household equipments and all that. Bonded neodymium ones are sensors and complex shapes. So these are some of the things which I would like to tell your audience.
Yes, sir. So there's one rare metal which you have spoken in this conversation, and that is dysprosium, and that is somehow both the hero and the villain of this entire story. So can you explain the trap?
Excellent. Now this is the most important question. Normally, these neodymium magnets have high torque density. Okay, let's talk a few attributes of neodymium magnets before we go into dysprosium, why this is added. Okay, high torque density, they are compact motors, they have high efficiency, and they can be miniaturized. Okay, however, they have their own problems, which is your heat sensitivity, which I mentioned to you, and geopolitical sensitivity, and then their poor corrosion resistance, and they require coating like nickel, zinc, epoxy coatings and all that to help prevent corrosion. Now we add dysprosium to improve the temperature performance. Now, as I mentioned to you, dysprosium has got a geopolitical problem. It also has, of course, it improves the corrosion resistance, but however, the remanence is brought down. So how can we have a situation where remanence is also there as well as temperature resistance? So this is where we do a lot of, what we call innovation, how to bring it. Before we go into these innovations, which I'm going to talk to you right now, China's licensing system, in they specified the following magnets: SH, UH, EH, and AH. These are the various, what you call heavy rare earths families and all, which are under licensing, which your audience should also note, because some of these are imported into India. So these are the ones which are under license. So now let's come back to dysprosium. How do we reduce the dysprosium content from 5% to 1 or 2%? Because in the process of doing so, you can restore the remanence which is lost because of dysprosium. Dysprosium is anti-parallel to iron. So it goes in the opposite direction. It removes the magnetic field to a large extent. Okay, so how do we restore the remanence, and without sacrificing on the, the temperature resistance? Now, in a magnet, there are grains, and grains have grain boundaries. The maximum of this coercivity, what happens is the temperature resistance comes down is along the grain boundaries. Instead of putting dysprosium in the entire length and breadth of the material, which is a waste, okay, why don't you put it only on the grain boundaries? In the process, the 5% dysprosium can be brought down to 1 to 2% because you're using it economically. You're optimizing the usage of dysprosium. Instead of wasting it on the entire length of the magnet, which is not required in a way, okay, put it only along the grain boundaries. What do? You put it on the surface and then make it diffuse into the grain boundaries. That's what dysprosium. Now, this is called the grain boundary dispersion, GBD. Okay. Now, because of this, dysprosium content can be brought down. Okay, that is one point. Then the second is grain refinement. If you make the grain size smaller, what happens is it has got automatic anisotropy, which is what is called as a resistance to demagnetization. It improves the coercivity. Okay, so there is a resistance to demagnetization improves if you make the grain size smaller. How do you make the grain size smaller? Now, this is an interesting thing. It is what is called as HPV, HDD, HDDR, which is hydrogen disproportionation, desorption, what you call recombining, which means if you use hydrogen, what happens is the magnet becomes into a powder. If you put hydrogen into the magnet, it becomes a powder. Now, once it becomes a powder, and then you remove the hydrogen, it has served its purpose. You take its desorption, you take the hydrogen back again, and then you recombine them. Okay, HDDR, hydrogen disproportionation, desorption, and recombination. If you do this, so whatever is a magnet which comes has got a lower, smaller grain size. So that is important. The grain size can be brought down by this HDDR, which I mentioned to you just now. It's an interesting technology. Then what is called as jet milling, and using helium, you can bring it down. Then there is also another thing called grain boundary phase engineering. Okay, these are the various steps in which you can improve the coercivity. One is the grain boundary diffusion, which I mentioned to you, putting the dysprosium only along the boundaries. The second one is increasing the grain size through HDDR, which I mentioned to you just now, and jet milling, make it into smaller pieces through helium and so on and so forth. That's the second method. The third method is grain boundary phase engineering. So what does it mean? If you have a long chain of people, one after the other, if one fellow goes, the other fellow also goes around with it. So it's called concatenation. It forms a chain. Now, if you break that chain, that each person is isolated from the other. If one of the persons is affected, the other person is not affected. So what do you do in this? You isolate all the grains, so that when one of them has a problem, the other one does not catch on to it. So this is grain boundary phase engineering. By how do you do this? How do you isolate grains from each other? So you use what is called as indium, copper, aluminum. These are the various alloying elements and all that stuff. So all these three processes will help you to improve the coercivity and reduce the usage of dysprosium.
So this is the part I really found very fascinating, very interesting. So you said that the winners use less of the scarce material, not more. How can clever metallurgy beat brute force chemistry, and why is that a national security strategy as much as an engineering one?
I told you dysprosium can be brought down the way I told you just now. There are other ways, like what this I mentioned to you 2 or 3 names. I mentioned to you about ABB, synchronous reluctance motors. Then I have also mentioned to you about the Chara, which is also what is called as switch reluctance. Now, listen carefully. This is a bit of physics and science. You must.
Nice. Like you're making it a bit simple by explaining.
Which is a bit of physics and science, so and also engineering. So please.
Engineering, yes.
Okay, now you have a stator, you have got a rotor. Stator is the one which is stationary. Okay, and the rotor is one which moves. That's how the motors move. Basically, the motor has got a stator and a rotor. Now, stator has got a magnetic field. Rotor also has a magnetic field. Okay. Now, rotors. Let's talk about the rotor. The rotor has got different path lengths of reluctance. The least reluctance is where the magnetic field passes. There are other areas where the reluctance is very high. So they are the paths through which flux passes very difficult. Okay. Now what happens is it's a general tendency. The rotor magnetic field tries to align with the stator magnetic field. And when I say align, it is the least reluctance paths of the rotor aligns with the stator magnetic field. Now, if that were to happen, then you have achieved your you have achieved your objective. Now, how can you make the rotor into a least resistance path, reluctance path, and a high reluctance path? By using what is called air cavities in the rotor shape, the rotor geometry. the cavities, and then the flux barriers. You allow the flux to pass through one direction only, that is anisotropy, not through other regions, no other directions. So you optimize the flux density or flow in one direction, not in the other directions. So by cavities, by flux barriers and all, you have a low reluctance path for rotor, and the way the geometry is done. So once you have these sort of things, and by mind you, the stator does not remain static in a way. It also rotates because of the alternating current and all that stuff. Okay. Now, when you combine these two, whenever the stator rotates, this rotor also aligns with it, and the least reluctance path aligns with this. Now, if this were to happen, what happens is, apart from the normal permanent magnets which generate torque, you also have the reluctance torque which is coming into play. If you have two torques working together, the reluctance torque and then the permanent magnetic torque, what happens is you can reduce the intensity of permanent magnets. You can make it up with the reluctance torque. So if you increase the reluctance torque, the way I mentioned to you just now, how can this is what is called optimizing the geometry. Optimizing the shape of the magnet, a permanent magnet which you put into the rotor, also optimize the position, the space, the location where you put this permanent magnet inside the rotor geometry itself, the air cavities, the flux barriers which you put inside the rotor, and the stator shape also. If you combine all this clever geometry, what you have is a situation where you can bring down the usage of permanent magnets, increase reluctance torque. Okay. Now this is what happens. Now this is one which is called the synchronous reluctance motor, which ABB pioneers and which others are also doing now. Then you have what is called the Chara. What they do, they have switched reluctance. What means to is there are poles inside what you call as a stator. They are excited alternately. Let's say one pole of the stator is excited. Now what happens is the reluctance motor comes closer to it, but before it can touch, okay, it's like a relay race. Before it can touch the stator part where it is excited, what happens is you switch off that excited part and you excite the other pole. Now this rotor goes to the other pole. So like this, this sort of not allowing it to touch, but switching it on to the next pole is a relay race which you practice. In the process, what is called switched reluctance. Now this also helps down in bringing down the usage of permanent magnets. So, these are some of the various things which we talk about. Then there are other ways of doing it also. Okay. With a lower, intensity magnet, okay, you can, there is a beautiful equation which is called as the speed of the motion is equal to 120 F by the number of poles. 120 into frequency divided by the number of poles. If you increase the number of poles, you can bring down the speed. Okay. Now what happens is if you reduce the permanent magnets to a lower magnet, where you are reducing the torque and the speed, you have to increase the number of poles. So by increasing the number of poles, there's a north-south pole in a magnet and other, increasing the number of poles, you can sort of design it in such a way that a lower magnet can replace permanent magnet. So that is one way. Second is power electronics. Whenever you do all of these things, what happens is the torque has a ripple, but that ripple can be removed by beautiful algorithms which are now power electronics which are coming into play. So then you also have the hybridization of the various magnets. You combine neodymium with samarium with ferrite, various things to reduce the intensity of permanent magnets. So I have told you how you can change innovatively, how you can change the geometry of the rotors and the stators. Okay. How you can also change the pole counts, how can you use power electronics, how you can hybridize the whole thing to, sort of the lower magnets trying to come up and replacing the higher magnets. There is also one more thing, the winding, like for example, what Enercon does. And how do you play with the windings, copper windings which are there in a stator? By increasing the number of windings in a particular stator, that's one, and increasing the thickness of the winding so that the resistance is lower. If you increase the thickness, the resistance comes down. The IR square losses, that is heat losses, comes down. So increasing the thickness of the of the copper wires increasing the number of copper wires to there, and placement of the wires. All of these can help you in having windings themselves take on the role of a permanent magnet.
I think after ages, I have like heard so much about physics. So it is very technical, but I think it will be very much helpful for the engineers and for the technology and all, so that they can develop and they can understand basically the idea behind it. So, sir,
So basically, from being a producer of magnets, where you are buffeted with the Chinese prices, the lowest prices, and also the vagaries of raw material and all that stuff, you go into an application platform, okay, where you sort of look at torque density. What is reliability you're giving to the customers? What is the magnetic performance you're giving to the customers? That's what you should be concentrating on: torque density, efficiency, miniaturization, thermal stability, supply sovereignty. How do you Indianize, and reliability, which the Japanese do. Japanese are important with regard to the way they have done the reliability, failure analysis and reliability. Now, I'm going to give you 5 or 6 parameters, which if you really want to go into applications engineering, okay, in fact, you should have 3 verticals. One vertical is basically the ores and what you call the separation, the refinement, the alloying and all that. Second is the production of the magnets. Third is the application engineering. That's the another vertical which any magnet producer should have. And what do you do in the application engineering? Okay, you start with the OEM, target the OEM, co-design the geometry with them. This is designing the geometry, rotors and stators which the OEM has. You do not have those. You only have the permanent magnets. You can play with the shape of the magnet. You can play with the position of the magnet which you put it in. That is your area. But then somebody else, it has to be a hand in glove relationship with the OEMs. So you do co-design the geometry, and then you qualify, and then you lock in. Once you qualify and you lock in, there is a customer stickiness. So what are the things which you should do? Okay, now one is you must be studying the BH curves. That is to say, how the magnetic field changes the what you call remanence and all that stuff, and what is the interplay of BH curves, as it is called. How does the remanence change with the magnetic field? So that is one study which you should do, so that you give reliability to the customers. Then you have thermal stability. When do the magnets become soft? At what temperature? So if you do that study, you are giving important data to the OEMs and the customers, so that they can plan accordingly. Then life cycle fatigue testing. How does your magnets respond to fatigue? Life cycles, so many RPMs and all that stuff. And rotor geometry and rotor integration, which I mentioned to you. Failure analysis and reliability. All of these things are very important. Redesign the geometry, hybridize, absorb the electronics. Electronics are important. The algorithms are important to remove all those torque ripples and all that stuff. So these are some of the things which you should be looking at. And as already mentioned to you, you should have 3 verticals: strategic materials vertical, magnets vertical, and appliances and assemblies. This is another vertical.
So very well explained and very deeply explained. So, sir, your line was that stop selling magnets and start enabling machines.
Yeah.
So,
You should not be a commodity supplier. You should be who is lock in step with your OEMs. You co-design the geometry. You hybridize. You absorb all these electronics and all, and you give them reliability and failure analysis, like the Japanese do. And then rotor geometry, rotor integration, all of these things.
But sir, doesn't this sound very philosophical? So what does it actually will mean for the company and for the country like India?
So what the Chinese are doing, I am saying that please localize the entire value chain, the ecosystem. Localize the entire ecosystem and the value chain. Right from, the ores and refinement and separation, then alloying, then sintering, then magnets, then, application engineering, and all of these, and co-development with the OEMs. This is what you should be doing to beat the commodity cycle.
Great. So, sir, moving on, is it really true that we can take a weaker, cheaper, lower risk magnet and still build a brilliant motor if we are clever enough about the machine around it? And because if so, doesn't that quietly undercut China's more advantage?
Look, this is what I've told you. How do you change the rotor geometry? How do you change the stator geometry? How do you redesign the magnets, the shape of the magnets which you put in? All of these, and I mentioned to you about the reluctance torque in addition to permanent magnet torque. Then I mentioned to you about changing the poles, changing the windings. Okay, now there is also one more thing. If you reduce, this is interesting, people should know, if you reduce the strength of the permanent magnets into some weaker magnets, also lower magnets and all that, what happens? Okay, now this is important, which you should note. These higher magnets induced by Faraday's law, Lorentz forces, they induce alternating currents, eddy currents in the stator windings. It is called back EMF. Now this reduces if you reduce the strength of the magnet. So it's in a way good. Sometimes reducing the strength of the magnet helps. And let's look at this. Now there are other things which I wanted to say. Okay. Now, when you extract magnets, you also, or when you extract the rare earths and all that, you get what is cerium. Is another rare earth. Why don't we use more of cerium? Cerium is given as a thing which comes out in a much bigger way. Okay, so using cerium magnets is also one important point which I would like to stress on. Now, I'm going to give you some futuristic thinking, at least in India, but elsewhere in the world, people are already accepting and doing it. It's called exchange spring composites. What happens is, now this is nanotechnology. You have a hard phase magnet, okay, and you have a soft phase magnet in between, and then you have another hard phase magnet. Between two hard phase magnets, you have a soft phase magnet. Now, and the length of the soft phase magnets between these two hard phase magnets is 10 nanometers, which is 1,000th the thickness of your hair. So this is nanotechnology. And when you go nano, strange quantum mechanics comes into play. Now what happens here is that when you are combining two magnets, one magnet has a high coercivity, other magnet has got a lower coercivity but a high magnetic field. Now, if you combine these two, what is called as exchange spring composites, at a nanometer level, exchange coupling happens because quantum mechanics. Now, once this happens, what is it? I told you this soft phase magnet has got lower coercivity. That means it has got a high magnetic field, but it reverses when you demagnetize it. So when both of these combine, this soft phase becomes high coercivity like the previous hard phase magnet. So hard phase magnet's coercivity rubs it on to the soft phase magnet. Now this is an interesting thing. You don't require big things to do. Just do this simple thing. You are through. Okay, this is another innovation which we are trying to talk about. Then there is another innovation, Halbach geometry. You don't do anything, you just change the geometry. What you do, you have magnets, they are positioned in a rotational sequence. Okay, now one magnet, then there is another magnet, the field rotates in a way, roundabout. If you position the magnets in a circle or whatever, in the rotational sequence. Now what happens is, they reinforce the one part of it, they cancel on the other side. They reinforce the magnetic field, magnetic flux on one side, and they cancel on the other side. Now this reinforced magnetic flux, if it can be put in a rotor and pass through a cavity, you will have again a reluctance effect. So this is called Halbach geometry. This is another one. Then I mentioned to you earlier samarium cobalt magnets. Remove the cobalt, okay, put iron, what we call it as nitrogen in it. Whenever you put nitrogen in any substance, the strength increases. So it's called samarium iron nitrides. So they also do a lot of good things. Now there is another interesting development. Manganese bismuth. Now this is critical knowledge, which if people hear, it's a great knowledge sharing, I would say. I told you this neodymium iron boron sort of coercivity becomes soft around 80 degrees centigrade or up to, and it goes on softly. But there are other kinds of magnets which increase their temperatures. As the temperature increases, their coercivity increases, their strength, their resistance to demagnetization increases instead of reducing. Neodymium magnets, it reduces, but manganese bismuth is a alloy which will increase its coercivity, which means as the temperature increases, demagnetization resistance increases. So this is another interesting point which I'll have. One last point. is alternate magnets. This is another concept, alternate magnets. You have two types of ferromagnets. You have anti-ferromagnets. In a ferromagnet, all of the magnetic moments are aligned in one direction. Anti-ferromagnet is magnetic moments are not aligned in any direction. They cancel each other. In the case of alternate magnets, here also the magnet moments are aligned against each other. They cancel their magnetization completely. However, one important thing, the electrons have their spin. If the electron spins can be up or down, the state of the spins. If the electron spins can be reinforced, they can combine together, align together in one direction. Despite magnetization being zero, as in the case of alternate magnets. That's that word, alternate magnets. Even if the magnetization is zero, but because the electron spins reinforce each other, you can have a higher, performance of the magnets.
So the next question that as you have mentioned that recycling here is not only about being green, it's now being about survival. So why is a warehouse full of old EV motors a strategic asset for India?
Look, there are two companies, Rocklink and Batex, in India, who are recycling the magnets. The scrap is generated in various places. Scarce, that is to say, when you shape the magnets, machine the magnets, you get a lot of scrap. 25 to 30% of whatever you do is scrap, machine scrap. So that is called swarf. Now, somebody should, collect those swarf and then make it into a magnet. Okay, then you have a life cycle reclamation, end of the life cycle reclamation magnets, and then closed loop chains. So all of these can be done. It can be done what is called as, when you have all this scrap, there is something called friction stir welding. Instead of melting the material, you go below the melting point and do what is called friction stir welding, and you can sort of sinter all these magnets together. So this is how you use, you recycle the products. Okay, and then you can also recycle the products through three other methods. Hydrometallurgy, where you use acids, to retrieve the magnets. And then pyrometallurgy, which is, smelting and roasting and so on and so forth. And, so these are some of the things which we do. And then also, as I mentioned to you earlier, hydrogen process of magnetic scrap. Hydrogen can break down the scrap to powder, and then it can recombine. Okay, so these are some of the things which we do, and the Japanese have done that also. Japanese are known for thrift. Thrift is reducing the dysprosium content, which I mentioned earlier, and all of these, recycling, reclamation, friction stir welding, and then swarf, all of these sort of things. And it is important we do it so that, if we are not able to mining takes a lot of time, what you call as, separation and refinement and all take a lot of time. Why don't you, all the used magnets, why don't you start using them through this method which I mentioned to you just now?
So now the last question. So 10 years out, what has to go right for India to move from owing the sand on the beach to owing the magnet inside the machine? And after everything you have seen, are you actually optimistic?
Look, India has got monazite sands in Kerala, Andhra Pradesh, Tamil Nadu and all this. And we are told that 25 to 30% of the world's monazite is in India. These contain rare earth, oxides also, but unfortunately most of the Indian rare earths are light rare earths, not heavy rare earths. Okay, so that is one. Second point is, it also contains thorium. India is blessed with 25 to 30% of the world's thorium. Okay, now why don't somebody gets into the mining of this, extract thorium, which is basically breeder reactor, nuclear breeder reactors and all that stuff. Okay, instead of using imported uranium and all that, people can start using them along with all of these rare earths which can be coming out of it. Now, this is on the ores and the, mining and, refinement and sintering and then separation and all those sort of things. We should get into manufacturing the magnets along with the OEMs. We should do the, co-design the geometry of the rotors, of the stators and the magnets themselves, and get into the process of qualification and beat this commodity cycle. And we should be benchmarked not for the lowest price, but for the one where, we have, we produce high value magnets and all, which can be used despite whatever the commodity cycle be.
So very well explained. You have explained the science behind it.
Just one last point.
Yes,
Okay.
sir, please.
There is a company called Niron Magnetics in US. Okay. Now, I mentioned to you that the maximum BHmax or what we call power density is 400 kilojoules per newton per meter cubed for ND-FeB magnets, the neodymium ion band. They are also producing nitride magnets, which have got 1000 kilojoules per nm cubed per normal per meter cubed. So this is something which is going to help. There is also another one. I mean, these are all the things which we should be doing it. Nitrides. Okay, Niron Magnetic is already doing it. Most of the examples which I have mentioned, they are not theoretical examples. They are all practical ones which people in the world are doing it. So if they are doing it elsewhere, why can't we do it here? Then there is another one. It's called the tetratenite. Most of the meteors which are coming into India or the rest of the world and all that meteor, they have this element called tetratenite. It is also rare earth in a way, and it can have a BHmax of 335 kilojoules per meter cubed. Okay. Now, why don't we do tetratenite in laboratory and then start commercializing it? People are already doing it.
So that, as I mentioned, like you have explained very briefly all the things from the basic to the science behind it, the implementation, the live examples, and the motivational that if others can do, why can't we do? However, we are not behind any other country or any other. India is capable of everything, and also the importance of a magnet, which is basically not been so much been talked about. So this was a great conversation.
Summarized in one sentence, we are not in the should I say the business of magnets, but we are in the business of guaranteeing outcomes and reliability to the customers, which is torque density, thermal stability, efficiency, miniaturization, and sovereignty of supplies and reliability. So this is what we should be giving to the customers and to the OEMs.
Yes, very well said. Thank you, sir, for your inputs.